Welcome everyone to the course Materials in Sports. In this course, we will explore how the choice and engineering of materials play a crucial role in athletic performance across a wide range of disciplines. From running shoes to tennis rackets and swimming suits, material selection can make the difference between marginal gains and breakthrough achievements. Our focus will be on understanding not only the fundamental properties of these materials, but also how they translate into real-world performance advantages. Through practical examples, we will highlight the direct link between material characteristics such as stiffness, weight, elasticity, durability, and the demands of specific sports application. I would like to start with pole vault, as just recently the Swedish champion Armand Duplantis broke again the world record. Pole vault is a very relevant example of how materials performance are intertwined. This figure shows how Olympic records in pole vault 8 have progressed over the past 120 years alongside change in pole construction. The graph was originally published in Nature Materials in 2012. Before examining the data in detail, let's take a brief detour into the World Athletic Federation regulations on pole design. In official competitions, the rules sometimes restrict the materials, technologies, or features of equipment and clothing. Pole vaulting, however, is relatively open. Athletes can choose poles made of almost any material: wood, bamboo, metal, fiberglass, or carbon fiber composites. There are no limits on pole length or diameter, which are left to the athlete's preference and safety. That said, a few restrictions do apply. The pole cannot include moving parts or mechanical system, must remain a single passive element. Structural modifications intended to boost performance, such as external rings, texture grips, or projections, are prohibited. Historically, poles were made from solid wood or bamboo up until the 1950s. For a short period, metal poles became common, as you can see from the graph. From the 1960s onward, however, the sport was transformed by the arrival of fiberglass and later carbon fiber composites. The transition to composites coincides with dramatic improvements in the Olympic record heights. One reason is that composites allow manufacturers to fine-tune mechanical properties to match an athlete's needs. By carefully layering glass and carbon fibers in control orientations within a thermosetting resin matrix, they can produce lightweight poles with precisely tailored bending stiffness. Unlike metals, which are isotropic, the same in every direction, composites can be engineered to be anisotropic, meaning their strength and stiffness vary depending on fiber orientation. This makes them highly efficient under bending loads. Compared to wood, composites also enable the production of hollow poles, which are not possible with solid timber. While metals can also be hollow, composites have the advantage of much lighter density, about 1.5 grams per cubic centimeter, similar to plastics. For comparison, aluminum is around 2.7 and steels are above 7 grams per cubic centimeter. This means composites are significantly lighter while providing the necessary structural strength. As we will see, the shift from wood to metal and then to composites is a recurring theme in the evolution of sport equipment pattern, also evident in tennis rackets, baseball bats, and other gears. The case of tennis rackets will be discussed in more detail in Lecture 3 of this course. If you want to know more about pole manufacturing, I suggest watching the video I left in the additional material of this lecture. In the video, the manufacturing of mother poles made of fiberglass and carbon fiber composites is shown. Now, let's talk of another great example of how materials can shape athletic performance, this time in swimming. At the Sydney Olympics in 2000, Speedo introduced a revolutionary swimsuit inspired by shark skin. By using biomimicry, the design team created a full bodysuit that copied the texture and the hydrodynamic efficiency of a shark's surface. The results were striking. Athletes wearing the suit won 83% of the swimming medals that year. Built on that success, Speedo in the 2004 Athens Olympics released an upgraded version called Fastskin FS2. Swimmers in that suit went on to claim 47 medals. Then came the 2008 Beijing Olympics, and with it, a real game changer. Speedo unveiled the Razor bodysuit, designed with polyurethane panels and developed in collaboration with NASA research centers. The impact was immediate. In that one Olympics alone, swimmers wearing the suit broke 25 world records. To put that in perspective, across all track and field events combined, only 5 world records fell. By the end of the Games, almost 95% of swimming gold medalists were wearing the laser suit, celebrated by some as revolutionary, but criticized by others as unfair. But what makes shark skin so special? To understand the biomimetics behind this innovation, we need to look at how real sharks swim. In the image, you can see how shark skin appears under a microscope. Shark skin is covered with microscopic structures called dermal denticles. These denticles are tiny, tooth-like scales that reduce drag by channeling water efficiently over the shark's body. Interestingly, they make the skin very smooth in one direction while being rough overall. A paradox that results in a lower hydrodynamics resistance. The effect: less energy spent per stroke and more speed for the same effort. But why would a rough surface like shark skin be more efficient in swimming? The answer lies in fluid dynamics, and it is illustrated in this figure. In turbulent flow regimes, drag forces typically increase due to chaotic eddies and vortices. However, when we compare the two images, one showing flow over a flat surface and the other over a structured surface with riblets, like those found on shark skin, a key difference emerges. The riblets disrupt large vortex formation and reduce the ejection of eddies into the outer boundary layer. This means less momentum transfer between the moving swimmer and the surrounding water. In other words, less energy is lost to turbulence. Think of it in this way: a thin layer of water becomes attached to the shark skin surface, forming a kind of lubricating film. The surrounding water then slides over this stable water layer rather than directly over the swimmer's body. It's not water sliding on skin, it's water sliding on water, and that makes all the difference for sharks. However, the explanation provided by Speedo's researchers was met with skepticism by some in the scientific community. Among the critics was George Lauder, a professor of ichthyology at Harvard University. After analyzing the suit under a microscope, Lauder observed that it lacked the distinctive microstructure characteristics of real shark skin. This led to the emergence of alternative hypotheses regarding the source of performance enhancement. One prominent theory was buoyancy, the idea that the suit may help swimmers maintain a more optimal position in the water, thereby reducing drag. The suit was not made of ordinary fabric. It consisted of laminated textiles engineered to be smooth, water repellent, and strategically compressive, likely contribute to improve hydrodynamics in ways beyond simple biomimicry. This image comes from Speedo's official patent. It shows the structure of their laminated textile. At the base is a knitted fabric coated with a continuous layer of polyurethane. That coating seals the weave of the fabric and creates a smooth water-repellent surface. When the suit is worn, tiny pockets of air get trapped between the fabric and the polyurethane layer. What's remarkable is that the air stays there even after the swimmer dives into the pool. This can give the athlete a slightly buoyancy boost. And in competitive swimming, just a few millimeters of extra lift, keeping the body a little higher in the water, can make the difference between winning and losing a medal. And now we reach the end of this story. In January 2010, the International Swimming Federation introduced new regulations that effectively ban the use of Speedo lidosuite and similar high-tech swimsuit from official competitions. The material used for swimsuit can only be made of textile fabric. For the purpose of this rule, this is defined as a material consisting of natural and/or synthetic, individual, and non-consolidated yarns used to constitute a fabric by weaving, knitting, and/or braiding. Surface treatment of the textile fabric, any material added to the surface of the textile fabric, such as coating, printing, impregnation, shall not close the open mesh structure of the base textile fabric. The material shall be flexible and soft folding. The material shall be regular and flat. The material shall not form outstanding shapes of structure, such as scales. The new rules explicitly prohibit any surface treatment that closes the open structure of the underlying fabrics. And these mark a decisive move to restore the emphasis on athletic ability over technological advancement in competitive swimming. To recap, in this first lecture, we introduced the central theme of the course, the crucial role that materials play in sport performance. Through two key examples, the pole vault and the swimsuit, we began to explore how innovations in materials can transform both equipment and athletic outcomes. In the upcoming lectures, we will take a deeper dive into material science, examining the technologies, properties, and design strategies that drive performance in a wide range of sports. See you soon for the next lecture.